finding the missing young stars. Yeah. Okay. So.
Okay. Thank you very much for the nice introduction, and thank you very much for having me here today to present my work. So yeah, I'm going to be talking about the star formation in the galactic center, and particularly about young stars there and the overall star formation history. But the first question that we have, well, let's start with an introduction. The first question that we have is why the galactic center? So the galactic center is super interesting, but why we want to study the star population that we have there? So it's not only the galactic center here in our Milky Way, but it's also galactic nuclei in general. So they are super interesting. They are extreme environments, and we can find there many extreme phenomena. So for instance, we have normally supermassive black holes. We have high stellar densities, high magnetic fields, tidal forces, a lot of gas, pressure, so turbulence, high temperatures of the ISM. So many nice things. And we really need to know more about that and how the stars are being formed there and all the processes related to stars that we can find in these extreme environments. So for instance, just to motivate the topic here, you have M87, the supermassive black hole. So it's really well known and it's a hot topic now to study and understand galactic nuclei. So let's try to know more about them. But the main thing with galactic nuclei is that we have a problem. So they are very far away. So we cannot really resolve individual stars there. So the thing is to try to have a template in order to know more about them. So even if we go to Andromeda, as you can see here, so this is a comparison between Andromeda and the moon. So you can see how the center of Andromeda is this tiny spot here. So it's very complicated to study these kind of things. But the thing is that we have a solution. We have our Milky Way center, as you can see here, and it's 100 times closer than Andromeda. So it's a unique template in order to know more about how these extreme environments are behaving. So if we do this game and we put the galactic center onto Andromeda, this is what we see. So it's really the whole size of the galaxy. It's going to be the size of the galactic center here. So that's why it's very interesting. So galactic nuclei are far away, but we have the Milky Way to solve the problem. So once that we know that the galactic center is going to be very interesting, let's try to know where the galactic center is. So this is Madrid. So this is the skyline of Madrid with the latitude. And here is the galactic center. So it's a bit dark, you cannot see it, but the thing to try to identify the galactic center is to go and to look for the Sagittarius constellation. It's here. It's also called the teapot. And why is that? It's due to the shape. So you can see here, it looks like a teapot more or less, and now it's even clearer. So, and this part of the teapot is going to point towards the galactic center. Actually, this is like a simulation of today's night. So it's around 8 p.m. more or less. The only problem is that the elevation of the galactic center is quite low. So it's not really easy to identify the galactic center from here, but at least you know that it's visible. The galactic center is only 26,000 light years away from the Earth. So it's close, and it allows us to resolve individual stars. And this will enable in detail analysis of the structure and stellar populations that we can have there. And we can then compare this with other galactic nuclei where we only will have integrated light, and we can try to infer properties there. So it's a perfect laboratory. So once that we know that the galactic center is cool, let's try to know more about the structure that we have there. So the nuclear bulge. So this is a nice near-infrared Spitzer view of the galactic center, well, the galactic center, the innermost region of the Milky Way. Here you have, this is the real galactic center where the supermassive black hole is, Sagittarius A star. And the first thing that we can notice here is that we have like a flat structure, and it's different from the surrounding area. It's darker. So this structure, it's called the nuclear bulge of the Milky Way. It has a radius of around 200 parsecs, more or less, and a scale height of around 50 parsecs, roughly speaking. And it's completely different from the surrounding area, that is the galactic bulge, or it's better to say the galactic bar, because actually the Milky Way's bulge, it's a bar. So here we have around 10 to the 9 solar masses of stars. So we have many stars in a tiny volume. So it's nice to know how the stars are behaving there. This is again the same, well, not the same picture, but it's also a Spitzer 3.6 micron image of the nuclear bulge. You can again identify here this flattish structure with this size that I told you before. And within the nuclear bulge, we have two different features, two different structures. So the first one, it's called the nuclear stellar disk. So it's a disky structure. Actually, we don't really know the shape because we have a lot of challenges to study the galactic center. I will go into detail later. But the thing is that, yeah, we call it disk, and it has a radius of 200, 150 parsecs, more or less. And we have here something like 10 to the 9 solar masses of stars there. And then in the middle of this thing, we have a completely different structure. It's called the nuclear star cluster. This is the most dense environment, stellar environment of the galaxy. Here we have 10 to the 7 solar masses of stars in an effective radius of around 5 parsecs, more or less. So this is tiny in comparison to the other thing, and we have many, many stars there. And if we go to the very central region, there we find Sagittarius A star, the supermassive black hole. So now you know how to identify the nuclear stellar disk. The nuclear bulge is just this disky structure that we see in the galactic center. And now let's try to learn how to identify the nuclear star cluster. So it's a bit dark. I don't know whether you can really see it well or not, but this is the innermost regions of the galaxy. This is the nuclear star cluster, and particularly here. And the thing is that you can try to identify the nuclear star cluster just trying to look for South America. So this is the shape, as you can see. Or maybe you can't because it's a bit too bright maybe, but this is the idea. So here you are, you see the contour, the shape, and it really looks like South America. So this was one of the first things I noticed when I started to work with this, and it's funny. So at least you have like a way, now it's, yeah, now it's darker, so now you can really see it. So once more, well, now, yeah, here, so. It really looks like South America due to differential extinction and due to many effects that we have there. Okay, so we have these two structures, the nuclear stellar disk and the nuclear star cluster, and we have another thing surrounding the whole nuclear bulge of the Milky Way, and it's called the central molecular zone. So it has a radius of around 300 parsecs, more or less, and here we have more than 10 to the 7 solar masses of molecular gas, quite dense, and you can see that we have many, many clouds all over the place. So we have, for instance, Sagittarius B2, we have Sagittarius B1, several clouds here, the brick here, which is an S cloud, and it's a star-forming region. Actually, the galactic center is the most prolific star-forming region of the galaxy when we take into account the small volume that we have here. Because remember that this is only like 200, 300 parsecs across, more or less. And it partially overlaps with the nuclear stellar disk, as I told you before, because this is more or less the size within the central molecular zone of the nuclear stellar disk. Okay, so now we know the place, we know that it's very interesting. So let's try to know the challenges that we can find here. So the first one, it's pretty clear in this movie. So we are going inwards and we are going towards the galactic center. And what you can see is that we have a lot of stars, a lot of gas. So we are going through the galactic disk. And in the end, we are going to end up in the nuclear star cluster. So we are almost there. So here you see South America. So yeah, this is the nuclear star cluster of the Milky Way. So it's close, but it's also far away. And we have the first problem. It's the anatomy of the Milky Way. So we need to go through all the spiral arms, then the galactic bar, and then finally we will end up there in the galactic center. So we are going to have a lot of contamination. So foreground stars that don't really belong to the galactic center, or we are not going to be interested in them when we are trying to understand the galactic center. So here it's even clearer. So this is what we have. Here is the sun, and 26,000 light years away, we will have the nuclear bulge here, this red spot here. And the thing is that we have the spiral arms, and we also have compact giant molecular clouds and a lot of stuff here. So this is a problem, and we need to take this into account in order to get information from the stars there. So it's not only that, but the thing is that if we go to the visible, so this is what happens. So this is exactly the same region, and you can even identify some stars. Have a look at this one, so it's there. But the thing is that with visible light, we cannot do anything, in principle, because we are completely blind there in the galactic center due to all the extinction that we will have from here to the galactic center. But yeah, what we have, it's the near infrared, as you can see here. So here we really are able to see many, many stars, and we can retrieve some information from the star population just going to the near infrared bands. Here it's even clearer. So if we go to the B band, for instance, we are going to have 30 magnitudes of extinction. So it's really like a black hole. We cannot see anything. And here it's, yeah, you see just the pattern of the gas and dust that we have along the line of sight. But in the near infrared, we have a bright spot here, and this is the galactic center. And the extinction, particularly if we go to the K band, it's going to be around 2.5 magnitudes, and we can do something there with that. It's not only the extinction, but another problem that we are going to have is the differential extinction. So in principle, if we are observing the galactic center, we would expect to have a homogeneous distribution of stars all over the place. So this is just a random field out of one of the surveys that I will introduce you later, the Galactic Nucleus Survey. And the thing is that this is not homogeneous. You can see some spots, dark spots there, and this is due to the fact that we are going to have differential extinction. So we have material along the line of sight, particularly there due to the central molecular zone. And this is a problem that we need to know how to address. So the extinction curve is going to be fundamental. And then we also have many, many stars there. So it's not only the foreground stars that we are going to have, and we need to distinguish them from the stars from the galactic center, but it's also the thing that we have many stars there. So this is just a random field, the Galactic Nucleus Survey. And even here, where we don't have any structure that we know, there are many stars. And the situation is even worse if we go to regions where we know that we have something, like the two massive jump clusters that we have in the galactic center. So this is quintuplet and this is arches. And here you can see that we have many more stars, if that is possible. So even with high angular resolution observations, we are going to be limited by these very high densities, and we will be able to only observe normally giant stars because they will be dominating the light. So it's very challenging and very complicated to go up to the main sequence star, for instance. So we are going to be limited by these giant stars. So now let's introduce a bit the state of the art. So we have many surveys for the galactic center. So we have TUMAS, we have PVB, UKITS, FITSER, NICMOS, but they all have problems. The main problem is the low angular resolution, because as I told you just a second ago, we have there a lot of stars, and we need very, very high angular resolution in order to know more about the stars that we have there. So they are normally not enough. The best one was the VVB survey. It was prepared for the galactic bulge, and the angular resolution is 0.6 arcseconds more or less. So with this, we could do something for some regions, but it's not really enough. And then for regions where we have high angular resolution data, for instance, using HSP, the problem is the short wavelength coverage. So we need to have several bands in order to try to infer the properties of the stars that we are looking at there. So this is clearly not enough. But the thing is that we have the Galactic Nucleus Survey. So this is a survey. The PI is Rainer Schödel, and we were working on this, and we published the survey in 2019, 3 years ago. And with this, we can really improve the state of the art. And the main results that I'm going to present here, they are related to this Galactic Nucleus Survey. So now let's talk a bit about the survey. So this is, again, the Spitzer image of the innermost regions of the galaxy. And here you can see the skin of the regions that we are covering with the Galactic Nucleus Survey. So just to put you into context, here we have the nuclear star cluster and the supermassive black hole at the center of the whole thing. So with the Galactic Nucleus Survey, we cover different areas. Some of them, they are in the inner bulge, the inner galactic bar. Then we also have some regions in the transition area between the galactic bar and the nuclear bulge. And finally, we have the innermost regions of the nuclear bulge, as you can see here. So this is a summary of the Galactic Nucleus Survey. So in total, we cover around 50 fields in 3 bands, in 3 near-infrared bands, where the extinction is relatively low, and we can study stars, so JH and KS. In total, we were observing the galactic center for 50 hours, plus 11 nights in visitor mode, and it was 3 years of observation. We started in 2015, and we finished in 2018. And in total, we have more than 3 million stars here in this tiny region in comparison to the large scales of the galaxy. The total size of the Galactic Nucleus Survey is around 0.3 square degrees, which means something like around 6,000 square parsecs there. And the uncertainties are very, very good. And we are even improving this with a second release of the Galactic Nucleus Survey that will show up soon, maybe in a year from now. And the thing is that the uncertainties here are below 0.05 magnitudes for J around 21, H 19, and KS 18, as you can see in these plots. So I told you before that the PVB survey was the best survey for the innermost regions of the galaxy before the Galactic Nucleus Survey. And this is a comparison between these 2 things. So the first one is the VVB, and this is the worst region ever. This is the nuclear star cluster. And now here you can see how we are really able to disentangle many more stars using the high angular resolution that we have with the Galactic Nucleus Survey. So this slider was prepared by ISO for a press release that we had in 2019. And it's impressive how we are really able to see many more stars using this. And this also applies for the other regions, but it's less spectacular than here. And now, finally, this is like a walk around the galactic center. So this is the central field of the Galactic Nucleus Survey. Here you can see some of the clusters that we have. We know this is quintuplet, and you can see many stars. This is the nuclear star cluster, South America again. And this is arches, another young clusters that we have in the galactic center. You can also notice the differential extinction that I told you before here. And yeah, this is the innermost region. So we really have 3 million stars here, and we can do many things with them. So now I'm going to let you know how to work with this nice data set. So we have the data set now, and we need to know the tools to work with this. So we are going to have 2 main tools to work with this thing. So the first one is the CMDs. They are color magnitude diagrams. And the other one is luminosity functions, particularly in K-band, because it's where we are going to have the lowest extinction. So this is a color magnitude diagram, particularly here I'm showing Ks versus H minus Ks, and you can see how we have different features here. And now I'm going to try to explain you how to work with these things. So we are going to have different effects here, and they are going to be combined, and we need to know how they are working. So the first effect for the color magnitude diagram for the stars that we are going to see, there is the distance effect. So here I am assuming a star population of 12 gigayears, a metallicity in agreement with the metallicity that we expect for the galactic center, supersolar metallicity, and without extinction to make things easy now. So this is the first distance. I am started with 3 kiloparsecs, and if I move this, this is what happens. So depending on the distance, we are going to have this effect. We are going to go towards faint magnitudes here for a given star population. So distance will go in this direction. Then we are going to have another effect here, the extinction. And this is going to be quite important because we are going to have some degeneracies here. This is again the same star population as I showed you before, 12 gigayears, the same metallicity, because we need to assume something. And then also the distance to the galactic center, 8 kiloparsecs from the Earth. And now let's start with 0.05 magnitudes of extinction in K. And if we increase this, this is what happens. So actually we are following the reddening vector for the stars that we have for this given age. So now we have 2 things. We have the distance going down, and then the extinction in this line with some slope, but a bit of degeneracy there. So this is one of the problems there. And then finally, probably the most important effect is the stellar population. Depending on the stars that we have there, also taking into account different metallicities, but now I'm going to be focusing on ages, we are going to see different features there. So let's start with 50 million years old for these stars, and then 100 million years, 250, and so on. And you can see how we are going to see different things there. And this is important in order to retrieve information from the stellar populations that we have. The only problem is that everything is going to be completely mixed up, and that's also a problem. But this is actually one of the results of the Galactic Nucleus survey. So here you have 3 different regions. So one of them in the inner bulge, another one in the transition region, the middle one, and then one in this red area, the central region of the Galactic Nucleus survey. It's this one. The first thing that you can notice when you compare the different color magnitude diagrams is that they are different. So this means that we are going to have different populations there. Just using this, it's going to be very complicated to really know what we have there, because we have a lot of degeneracies, as I told you before. But the thing is that this will give us some information. For instance, if we zoom in here, this is one of the color magnitude diagrams. It's pretty clear that we have different features. So if you remember, the first problem that we had to observe the galactic center was that we had all the galactic disk in front of us, in front of the galactic center. And here you can see some stars due to this effect. So in principle, we think that we have 4 spiral arms along this line of sight. And here you can see how they are behaving here. One of the good things of the extinction is that we are going to be able to remove the contribution from the spiral arms just using a color cut here, because they are going to have a different extinction. And this is one of the good things of one of the main problems with this extinction. And then once we are at the galactic center, so we can find different features here. So for instance, we have the asymptotic giant branch bump, this bump we see here. Then we have the red clamp feature, and this is going to be super important because red clamp stars, they are stars that are, let's say, like in a, but instead of being burning hydrogen, they are going to be burning helium there. But this feature is quite stable, and they are more or less standard candle in the sense that we can really use them to compute extinctions. So this is like one of the solutions that we're going to have there. Then we have another feature, it's the red giant branch pump. It will change with the age, and it's going to be also useful to try to determine ages. And then finally, we have main sequence stars and ascending giant branch stars down here, and the main sequence would lie around here, but we cannot really see that with this data. So we need to wait a bit to the new telescopes. So that was the first tool, the color magnitude diagrams. And now we have something a bit more precise, a bit easier, because instead of having the color magnitude diagram with 2 dimensions, so K and the magnitude and the color, now we have something with only 1 dimension. It's the luminosity function. And here we can see if we compare different ages. So here we are going from all stars, all star populations to young star populations. So here we start 8 gigayears, 11, 14, and we see how they behave in a similar way, more or less. And we can see some features here. Again, the same features I showed you before: the symptotic giant branch bump, the red clamp, and the red giant branch bump. And here we see how these features and the relation between them are going to change depending on the stellar populations that we have there. And this is very, very important in order to know more about the stellar population and the star formation history that we have in this extreme environment. With luminosity functions, we are going to have different advantages. So the first one is that we are going to be less affected by extinction, because for the color magnitude diagrams, in the best case, we can use H and KS, but H is going to suffer more from extinction than K. And the thing is that if we are able to use K, we are going to have many more stars, and it's going to be easier to constrain the stellar populations there. So we are going to have a deeper photometry in KS. And then we, again, I said that before, we have something that it's only 1 dimension instead of 2. So it's easier to compare this with theoretical models. So now that we know the Galactic Center is cool, we have the Galactic Nucleus Survey, and we know the tools, let's try to know more about the stars in the nuclear stellar disk particularly. So first of all, I want to motivate this, and I want to motivate the star population and the star formation that is happening there in the Galactic Center, comparing it with the Milky Way as a whole, and just to let you know why the Galactic Center is so important for the galaxy as a whole. So the first thing that we have is the nuclear bulge, the nuclear stellar disk. It's here in the center, but now the current picture of its formation is due to gas and dust that is going to be funneled towards the innermost regions due to the galactic bar. So the bar is moving, and we are going to have all the gas and the dust that we have from the galactic disk. And this gas is going to be inwards, and there we are going to be forming like rings of gas and dust, and we will have star formation there. And this process will continue, and we will be growing the nuclear stellar disk. So this is more or less the current picture that we have of this using external galaxies, particularly the Timer survey, because as I told you before, the Milky Way is very complicated and we don't really know the shape of the nuclear stellar disk. But at least we can use external galaxies, also now the other way around, to try to know more things about our own Milky Way. So this is the inner region of the nuclear stellar disk, as I showed you before, and this is the region that we studied to try to infer the star formation history that we have for this nuclear stellar disk. What we did was, first of all, we used color magnitude diagrams. So the easiest thing to do is, first of all, to remove the foreground population. That's here. It's this red cat that I give here. And then we used red clamp stars, the red clamp features. Here we have stars with more or less constant intrinsic colors. And the idea is to produce extinction maps, like this one that I show here, in order to correct the K photometry, the KS photometry that we have for the stars there, to produce the luminosity functions. And then using luminosity functions and comparing the luminosity functions with theoretical models, we are able to reconstruct the star formation history. The first thing, just using again the color magnitude diagram, that we can see here is that we have like 2 features for the red clamp. It's even clearer if we go to JK. And this is due to the fact that we are going to have something that we didn't expect when we were studying this. And it's also visible here. So we're going to have 2 peaks here for the red clamp feature. So one due to all stars, and a secondary one due to a star burst 1 gigayear ago that was responsible for the formation of around 5% of the total mass of the nuclear stellar disk. And this is quite important, and it's part of the main results that we obtained when we reconstructed the star formation history of the nuclear stellar disk. So the first thing that we saw is that the star formation history is not quasi-constant, quasi-continuous as it was assumed. So this was like the standard paradigm of star formation there in the Galactic Center, but it was just obtained using very, very small regions in the Galactic Center with HST data. So now we really cover an important area there, and we are able to improve the results. And what we see is that it's not constant at all. So in principle, the vast majority of the stars, they are pretty old. Here we are seeing the comparison between two theoretical models to fit the luminosity function, just to avoid the systematics of the models. And the thing is that they both agree with that. So the vast majority of stars are going to be old. Then we have a period without star formation. So for some reason, maybe the bar at that time was not efficient as funneling gas towards the center, or maybe the supermassive black hole was active. We don't really know what happened there, but this is what we obtained. And then suddenly we have a lot of star formation here, and this is the 1 gigayear event that I showed you before that also left an imprint in the color magnitude diagram when we see this double red clamp picture that we have. And this is very important because it's interesting that for red clamp stars, actually they are more or less pretty constant in luminosity, but when you are in this region, near 1 gigayear. And this period lasts only around 100 million years. So this means that this star formation episode was very fast. So it was super energetic and very, very fast in a time of 100 million years, more or less. So it means that we also have had a lot of supernovae going off here, and we estimated that number. It's like 10 to the 5 supernovae. And this is also important because maybe the galactic center was completely different at that time. And then we also have some more star formation here until now, basically. So this also means that the supermassive black hole might be quite old, because in principle, we need material there to grow the supermassive black hole. And we didn't have material except here, probably, at the very beginning of the history of the Milky Way. So that's why this was one of the things. And another thing is that maybe this recent star formation that we measure here could be responsible for the formation of this structure that are called the Fermi bubbles. They can be observed in gamma rays. And the idea is that maybe the star formation and all the supernovae that we had quite recently could be responsible for this. So maybe this is a picture of how the Milky Way could have been 1 gigayear ago, like this galaxy with outflows here. So maybe something like this happened at that time. So now we know more or less the overall star formation history that we have for the Milky Way, but let's try to know more about young stars, because one of the problems that we have many problems in the galactic center, so that's why it's so interesting. But one of the main problems is that was called the missing clusters problem there. The first thing is about the name. So missing clusters, it's not a good name for this, because in principle, now we know that stars don't necessarily form in clusters. So what we have is maybe association of young stars due to a given cloud of molecular gas being collapsing. And there we are going to have a star formation. And maybe within this cloud, part of the cloud will produce star clusters. But it's not the whole thing. So not all the stars will form in clusters. But the thing is that the name, the missing clusters problem, comes from the fact that in the galactic center, we only know 2 young massive clusters. And in principle, we have some indicators, these ones that I show here, saying that we need to have more young stars. And we don't know where they are due to all the challenges that we have. So we have a lot of stars, and it's very complicated to really identify spectral types there. And we cannot pay the price of spectroscopy everywhere. So this is quite restricted to small regions where we know that there is something interesting, because it's hugely expensive in telescope time. So the indicators of these young stars, they are, first of all, we have 3 classical Cepheids. They were discovered in 2011 by Matsunaga. We also have the star formation history, the one I showed you before, and you saw that we have some star formation, some recent star formation. And then we also have the Lyman continuum emission there. So in principle, when we combine this, it means that we are going to have many more young stars. And now, currently, we only know about 10% of the total mass of young stars that we expect in the galactic center. So this is the state of the art of the situation. So as I told you before, we know 2 massive clusters with a mass of 10 to the 4 solar masses, more or less. They are quite similar. Arches is younger, maybe 2-3 million years old, and then quintuplet, 4 million years old, more or less. And they are here, they are the green crosses that you can see in these pictures. And then another thing that we know is for sure the nuclear star cluster, and within the nuclear star cluster, in the innermost regions of this cluster, we also have star formation now, but this is like a slightly different thing. And then we also know many stars all over the place, more or less in isolation, but they are like 100 stars there. And it's not enough at all to account for the mass that we expect. So how to solve this problem? So we need to find where these stars are. And we have a promising candidate here. So it's the Sagittarius B1 region. So it's really a region to tackle the problem. As you can see, this is a galactic nucleus image from a press release that we got like 2 months ago. And you can see that this image is already quite impressive. So maybe something is here, it's happening here. So actually, just to let you know where we are, so this is the nuclear star cluster, Sagittarius A star, and if we go like a bit less than 100 parsecs away from the galactic center towards east, we have the Sagittarius B1 region within the nuclear stellar disk. And this is the region that we studied. But why Sagittarius B1? It was due to the fact that here, the first thing that we have is H2 emission. So we are going to have ionized gas. As you can see here, we have some bubbles here and here as well, also here. And this indicates that maybe we have hot stars there that are going to be young and something could be happening here. We also have 6 young massive stars that we already knew, part of these stars in isolation that I showed before. And we also have a supernova remnant nearby, like here, more or less. And you also need to take into account that the whole thing is rotating. So the nuclear stellar disk is not static, but it's rotating with a period of around 5 million years for this region here, for the Sagittarius B1 region with that radius. What we did was exactly the same thing, but now taking into account that we really want to know more about young stars. So first of all, we have the color magnitude diagram. Once more, we remove the foreground population and we use red lamp stars and similar stars with similar intrinsic colors to produce extinction maps. And this is the extinction map that we obtained for this. And then we used the luminosity function and we compared the luminosity function with theoretical models, but now paying special attention to the youngest thing. So actually for this, we used 14 different theoretical models, a linear combination of them, and Monte Carlo simulation in order to take into account the uncertainties of the process. And here in this range between 0 and 60 million years, we had 4 different models, 5, 10, 20, and 40 million years for these models, just to know whether we had some contribution of that. And this is the result. So we applied the same technique with the same models to 3 different regions. The first one is here, is Sagittarius B1, the A panel. Then the B is a control region in the central region of the nuclear stellar disk. And then the C is exactly the same region that we studied with the other paper that we published. But now we used again all these young models to know whether the results change or not. And the thing is this. So here you have the youngest stellar beam, and we find for Sagittarius B1 around 6% of the total mass being due to the fact that we have young stars there. If we compare this with the control region, there we have less than 1%. So something is happening here, and we have many young stars here. And then if we compare this with the central nuclear disk, this is practically the same thing as we saw when we use the other approach. So it's something like 3% of the total mass here being due to the fact of having young stars. But this is also what we expect, because in principle, we have arches and quintuplet there, and we are going to have more stars, but we don't know where they are. But it's not as important in terms of young stars as the Sagittarius B1 region. So the total mass of young stars that we measured for the region that we studied was more than 10 to the 5 solar masses. So it's really a lot. We studied this further, and what we did was to go to this small region here where we have the maximum emission from the 4.5 micron image using Spitzer, and there it means that maybe we have stars burning the environment, and we repeated the same game again. So we used the color magnitude diagram to remove foreground population, the extinction maps, and we used the luminosity functions, as you can see here, and again, the Monte Carlo simulations, and this is what we obtained. So again, we have now more than 7% of all the stars being due to the fact that we have this young stellar component. And we also tried to determine the ages, to estimate the ages for the stars there. And to do this, as I told you before, we used Monte Carlo simulation. So we used 1,000 different models, taking into account the uncertainties, and we repeated this game of fitting the 14 theoretical models. And this is the distribution of the contribution that we obtained for the youngest stellar models that we used, considering parsec models and also missed models. They are optimized for this kind of analysis. So if we go to the 20 plus 40 million years model, this is what we see. So yeah, we can have some contribution, but we have many models without the contribution of models, many Monte Carlo simulations without the contribution of these models. But if we go to the 5 plus 10 million years models, this is what we saw. So this is for parsec, around 4% of the total mass was due to this, and we found these models for practically all the Monte Carlo samples. And here with mist is even more what we have. So 7%. This means that we have around 10 to the 5 solar masses of young stars there with an age of around 10 million years. So we can now even constrain that this tiny, well, tiny, it's like 40 square parsecs, more or less. This region within the Sagittarius B1 region is really containing a lot of young stars. So this gives us a new picture of the star formation in the galactic center. So this is again the Spitzer view of the galactic center. And the good thing is that we have many clouds here, and we know that some of them have star formation, and one of them is Sagittarius B2. So Sagittarius B2 is a region where now we have a lot of stars being formed. So it's like a nursery. And we can even estimate the rate of stars being formed in clusters there. And it's around 40% of all the stars that are being formed there. So maybe we have some regions in the galactic center that are forming stars, like this one here. And then what happens is that the whole thing is rotating around the supermassive black hole. So the orbital time is 4 or 5 million years, depending on the radius that you consider. And then we have something like arches and quintuplets. So they are clusters that were formed in these kind of things, in these kind of clouds, let's say there's B2, sorry, and they have now an age of around 3-4 million years old. And while the whole thing is rotating, we are going to be having collisions between stars and also between stars and giant molecular clouds. And this will produce a dispersion, dissolution of the clusters. And this is the final stage of this. So maybe after one more revolution, 5 million years, we will have that arches and quintuplet will become something like the Sagittarius B1 region now. So we will have these regions with dissociated stars and clusters. And this is probably not the only one, because we need more stars to really account for the whole budget of young stars that we have in the galactic center. And we now need to look for more regions like this one. But at least it's good that we know one, and we know that this can happen. So this is probably the process. So now to finish my talk, I would like to give you some take-home messages. So first of all, the galactic center is a unique template to understand external galaxies, and we also can play the other way around. So for some reason, for some things that we cannot really see in our own galaxy, we can go to external galaxies to see them face on. Then the galactic nucleus survey is changing this game. So it's key to unveil the star population that we have in the galactic center. We have a star formation history there that was quite episodic. So we don't have a quasi-constant, quasi-continuous star formation history. So we have bursts of star formation, and particularly this big one, 1 gigayear ago. And then we also have that the Sagittarius B1 region is quite important in order to understand this problem related to the missing young stars that we have in the galactic center. And finally, to understand the picture of the star formation there, we have that young stellar associations will be dissolved rapidly in scales of around 5 to 10 million years. And that's all. So thank you very much for your attention. And I'm happy to take some questions now.
Hey, okay. Thanks a lot, Paco, for this wonderful talk. Do we have any questions in the audience? Yeah, we have many questions in the audience. Okay, so.
Thank you. Let's see if I can talk. Thank you very much for the very nice presentation. So I was wondering, because there were these model proposed by Dietrich Croisen, suggesting that when these molecular clouds approach the very center of the orbits, so they trigger, so that triggers the star formation. Yeah. So I was wondering how that fits into your proposed scenario of star formation.
Okay. Yeah, sure. That's a very nice question, actually. So I think that it's not completely clear the way of forming, well, the regions that are forming stars here. So, but the thing is that, yeah, we have all the gas being funneled towards the galactic center. And maybe we have these 2 points where we are going to have the gas and the collision, and there maybe we are forming stars. This is okay with this model, because in principle, well, with this model, with this picture of star formation there, because in principle, we don't really know where the young stars were formed. So the stars that we have discovered here in Sagittarius B1, the thing is that now they are there, but the age is around 10 million years. So, and the whole thing is rotating. So maybe they were formed here in a region next to Sagittarius B2, or maybe in the other way around here. So we don't really know that, and it's very complicated to really trace back the rotation of this, because yeah, due to the collisions that we are going to have there, it's complicated to derotate the whole thing. But this is compatible with that. An alternative model is the popcorn thing, this model with the central molecular zone and many clouds there. And maybe in every single cloud, we're going to have different densities, different pressures, and this will produce star formation there. It could also be. The thing is that in principle, we have another very interesting cloud here, and you know it very well. So it's the brick cloud, and it's being assumed, well, assumed. We didn't know about star formation there right now. But the thing is that there is this paper by Jonathan Henshaw last year. And maybe the thing is that it's too opaque, it's too extinguished, that we cannot really see that. So maybe there is something there, because he detected like an arc. And maybe this is due to the fact that we have hot sources there. And this will maybe point towards the other model about star formation there. But this is not really a thing that you could know in principle with this kind of analysis. So you need to go to other wavelengths probably and to know where the stars are being formed now. But it's compatible with this. I am not, yeah, this thing doesn't really care about the way of forming stars. The only thing we know is that now they are there. I mean, 1 million years, maybe they will be here. So who knows, depending on the rotation of the whole thing. Yeah, in principle, yes, but the thing is that we don't know the shape of the nuclear stellar disk, and this is another thing, because there are several possibilities for this. I am very much in favor of having a disk, and now a current analysis that I'm carrying out here points towards a disk. But the thing is that in principle, you could have spiral arms there inside. You could have like a bar, a mini version of the bar, or you could even have a ring of stars. And depending on that, yeah, so what we see now, and we have some papers about that, is that we have some stars going westwards and some stars going eastwards. And this means that the whole thing is rotating, and we also have some spectroscopic measurements using apogee, for instance, and we do see this line of sight thing, and we know that it's rotating. But the structure is not that clear. So maybe some of them are not rotating in the same direction.
Can I ask another question? Yeah. So from your results, if I understood correctly, so there's the majority of the stars are these old, no, belong to this old population of stars. Yeah. And then there are these small bursts, no, of that have been happening.
Well, here, for instance.
There, yes. So because there you compare the central nuclear disk, no, and Sagittarius B1. Yeah. So yeah. There has been like these multiple bursts, no, along the history, yeah. But definitely the biggest burst was about.
This is not fully, well, it depends on the region you are looking at. I didn't talk about this, but thank you for the question, because it's really useful in order to understand a bit more how this nuclear stellar disk was formed. So this is the central part. And for the central part of the nuclear disk, this part here, we do see that the vast majority of the stars, they are old. Let's say more than 80% of the total mass was formed 8 gigayears ago. But the thing is that if we go to outer radii, like here in Sagittarius B1, this is what we find. I only focused on this part, but here it's different. And this is very interesting, because this is probably due to the fact that the innermost regions were formed early. And then once we had that, we were growing the thing. So this is compatible with the new picture of having this inside-out scenario. And this is very cool, because, yeah, so maybe in this regime between 2 and 7 gigayears, we were forming this outer part, and it will continue like that. So this is compatible with that scenario, and that's why we don't find these intermediate age stars inside, but they are there for the outcome.
So have you any region just in between just that traces?
That would be, actually, I am working on that, but there is a problem. Well, a problem. The thing is the quality of the data. So as I showed you before, we were observing this whole thing, the Galactic survey, for 3 years, and we had good weather and bad weather. And some nights were not so good. And that's a problem, because particularly they cover some of these fields. So yeah. I have that, but it's not as good as here. For some reason, I was super lucky, because Sagittarius B1 was the best region out of the whole catalog. I don't know why, but the seeing that night was amazing. Mm-hmm. And then the second best region was the control field. And that's why I chose, well, I chose the control field in that way just for that, because I really wanted to compare something similar. with similar data quality, because otherwise you don't know. It depends a lot. If you cut your luminosity function for some reason, you also need to take into account completeness and many different effects that I didn't want to mention because they are complicated and it's not the point. But yeah, in that case, it depends a lot on the data quality, but we are working on that. And the thing is that for some fields, I've seen that. So maybe, but it's also like a mixture of everything. So depending on the field, maybe you can get different things. But yeah, that's work in progress.
Okay, thanks. Victor.
Thank you for a very nice talk. It was very clear, very well explained. I indeed have a couple of questions that you have already partially answered. One was about how this scenario that you are proposing of star formation in the galactic center could fit with the inside out scenario. If you can extend, you can say some words about it.
Sure. I'm going the other way around, sorry.
You already said that is compatible in some sense, but if you can.
Yeah, well, it's fully compatible with that because in principle, first of all, we have what I have just explained. So we have in the next slide here. So yeah, we are seeing this intermediate age population, and this makes sense with that scenario. And then the other thing is that in principle now, Sagittarius B1, yeah, we have young stars here, but it's pretty far, more or less, regarding the size of the nuclear stellar disk from the supermassive black hole. So it's what you would expect. Because in principle, well, this is only, yeah, we have a 3D space and this is a projection. And this makes our lives very complicated because one of the problems of this whole thing and the reason why we don't really know the shape of the nuclear stellar disk is that you cannot really estimate distances here inside. Because the only standard candle, and I don't like to call it like that because it's not really a standard candle that we have, is the red clamp stars. And with red clamp stars, in principle, you expect to have some degeneracy and you want to measure distances as small as 100, 300 parsecs, more or less, in comparison to 8 kiloparsecs. And you have extinction there. And the extinction and the systematics of the 0-point uncertainty are going to kill you. So that's why you don't really know that. But in principle, if you don't pay attention to that, we have this region, it's far from the innermost region. And maybe, yeah, this is like the edge and you would expect to have young stars there. But it could also happen something like arches and quintuplet, and maybe they are just in front of the galactic center. Well, in front. I mean, if you have a disk, you have the supermassive black hole in the middle of the whole thing, and here you have arches and quintuplet. Maybe, or maybe it's the other way around. They belong to the back side of the nuclear stellar disk. That could also happen. But yeah, estimating relative distances is very complicated.
Okay, the other question was about the origin of the population in Sagittarius B1. So have you thought about any way to track back the possible location in the galaxy? I don't know, considering photometry or...
You could do that. There are works doing similar things, of course, for arches and quintuplet, and we will try to do that. But for that, we need the next step of this analysis, and that is proper motions. Because this is like other part of this whole picture. If you have proper motions, with that, you are going to be able to identify co-moving group of stars. And if they have similar motions, proper motions, but slightly different from the whole rotation that you expect there, that will mean that the origin of those stars could be the same. And then you go and apply for a spectroscopy, and then you characterize the stars there. And this is like the way of playing this game. And we have already observed this with a second epoch of the Galactic Nucleus Survey, this region here, and we are now working on the reduction of the data. And once we have that, we will be able to see whether we identify co-moving group of stars. I would expect so, because in principle, we have estimated the age of these guys to be 10 million years, and maybe we have at least part of the whole star population, this young star population, going towards more or less the same direction. So once we have that, we can try to trace back the motion of this, and maybe depending on the age of the stars, that is not really well constrained, because I said something between 5 and 10, so it's not for sure, but you can try to guess more or less from here, maybe from there. But the whole thing, the whole idea of this is to try to see the different steps. So from these molecular clouds, it's not only clusters, but also stellar association. Then you go to something like arches and quintuplet, and then finally you end up in something dissolved, but still more or less close. And this is something like Sagittarius B1.
Being at the edge of the inner disk, you would expect them to have basically only radial projectional velocity and no component in that directions.
What do you
Because
mean?
I mean, if you look at the arches at the quintuplet and the arches and the quintuplet are in the inner region, they will have the other components. But if you are in the edges, like Sagittarius B1, or I see on the other edge, you have also a bright spot that you could use to test whether this is true or not. If it's on the edge, it will catch you just coming towards you or receding from you. So you don't have the proper motions are going to be a bit more complicated, I guess, in that region.
Yeah, that's for sure. But actually, we have applied for more data here. We would like to extend the Galactic Nucleus survey to know where we have a counterpart of Sagittarius B1 near Sagittarius C, for instance, that is there, and it could be. But yeah, let's see where we get the time. So we will know that before Christmas.
Okay, so Lee, you maybe want to know what the red supergiants in the 10 million. Okay.
No, not the red supergiants, right? Thanks very much for the great talk. I thought it was really interesting. I mean, what do you think the prospects are of sort of spectroscopically observing these kind of massive star populations that are in this sort of Sagittarius B1 region?
Spectroscopy is great. The only problem is that you need to have a good science case. And I have applied for data with CMOS to try to know more about the stars there. So it's mid resolution, low to mid resolution. But in principle, we will be able to really disentangle hot stars and cold stars just using the CO lines in the K band. And this is the next step. So I am also looking forward to having more data about this, because now we know that this particular region is a small region. It's well constrained, and we have young stars there. But we still have the problem. So we don't know who they are. So we have many stars there, and I cannot say, okay, you are young, you are old. You cannot do that by just using this approach, because it's a luminosity function. In the end, it's integrated light. So now the next step is to characterize stars there. And what I have done for that is to choose a magnitude range between KS11 to KS14, and to compute the number of stars, of young stars that I expect there, assuming the age that I measure for the young star population. And hopefully I will get the time, but let's see what happens.
Oh, that sounds super interesting.
Okay, so here's the question that he didn't make. If you have a very nice, I mean, a huge contribution from a cluster which is 5 to 10 million years old with 10 to the 5 stars, or solar masses, excuse me.
No, but
yeah, where are the red supergiants? They should pop up in your photometric data like very clearly, extremely bright in the K band. So you would expect a huge, I mean, you wouldn't get most of the most massive stars like the X sources that you talk about that were discovered, I think, by Muno using the X-ray stuff. So I don't think NICMOS, the Passion Alpha survey, went that far away. So that's why we're missing some stars, which I'm pretty sure there are a lot of more massive stars there, and it needs to be done. But where are the red supergiants? They pop up so clearly that you should see very bright stars there. I mean, with case about 6. Well, or
6, 7.
Or well, by that distinction, maybe 8.
There are two things here related to that. The first thing, it's saturation.
Yeah.
So that's the easy answer. So with saturation, I didn't say that, but we are using here galactic nucleus. The saturation in KS, it's something like around 11.5. But as I told you before, this region was extremely good. The CN was extremely good. And the thing is that the saturation here could be even worse. But the thing is that I took that into account using the Sirius catalog. So with the IRST telescope. And there, in principle, yeah, we are correcting that, but we are limited at around KS 9.5 without taking into account the extinction. And then, so we are missing those stars. This is one of the things. The other comment that I have is that I don't expect to have a cluster here. So I want to make that clear, because in principle, we have two different things. The first thing is in this current star formation picture, and we know that not all the stars are going to be formed in clusters. And the other thing is that we have something like 10 to the 5 solar masses here. And that's a lot, because there's a paper by Diederik Kreuzen, I think it's 2019. And there they estimate the upper limit of a cluster here in the galactic center, and it's 10 to the 4. So in principle, either we have several clusters and they are dissolved, and they cannot be really identified just using densities, stellar densities, because you have many things there. And it's important. I have tried. So it's not possible. Or the things that it's a stellar association with a cluster efficiency of around 30–40%, as we expect from the studies now in Sagittarius B2. And in that case, everything is going to be even more dissolved there. But the thing is that we expect to have bright stars there, but we haven't identified them. And then if you go to TUMAS or things like that, you also have a problem because you cannot rely on the photometry there. Because in principle, maybe one bright star there means 20 stars, 30 stars, 40 stars. I mean, it's very complicated to really see. Yeah, I have also tried to cross-correlate with galactic nucleus to see whether a given bright spot.
Red supergiants are very bright, so you won't be having within. I mean, it's very unlikely you will have two red supergiants.
No.
Closer, but if you have a red supergiant contaminated by other stars, so they are.
That's what I mean.
Many times more luminous than the rest. You will the light, even in TUMAS, being that bad, will be dominated by the red supergiant, probably.
Well, in principle, some of these stars could have already exploded, right? And maybe this is related also to the fact that we have some supernova remnants nearby.
Well, no, I mean, that's what I said. 5 to 10 million years is the realm of the red supergiants.
So how many stars would you expect?
Many. If you have 10 to the 3 to the 4 clusters going, star formation going on over the last 5 to 10 million years, you should see a lot of red supergiants. It's basically the stars you're going to see. You're not going to see the other ones.
Okay.
And just my last question: in your view graph you showed about the 2020 paper, there was a mismatch between the BASTI and the MIST models for the very early population.
Where?
Yeah. How do you explain that? Or I mean, how important or how good? You look at the BASTI and the MIST for the young from the young population. This is a huge mismatch there. Well, and actually, how reliable are those in producing these early populations?
Two things here. So the first one is that this paper was focused on the whole thing, so the star formation history, not about young stars. So, and actually here, the BASTI models, particularly, the lower limit is 30 million years. So this is a problem for these models. And then with Parsec, it was the release, I don't remember, 2.7, something like that, and they have improved that a lot since that moment. For the youngest stellar being here, I think I consider probably 2 models, something like that. So this was not optimized for that. And another thing, so I want to explain how I computed the numbers, because here you are just seeing the nice plot. But the idea was to average, taking into account these two models, just to take into account the systematics. So the mean is the value that you consider your result, and then the standard deviation, let's call it like that, between these two things, it's going to be the uncertain. So it's within the uncertainties. But now for the next study, in that particular case, we used MIST models instead of BASTI due to this, because they are optimized really for young stars. And we also used Parsec models. The new data release, I think here it was 3.6. And here, you can see how they both agree. And actually, this uncertainty that I estimated using the average and then the standard deviation, it's only 0.4.
So it looks like a problem with the BASTI models.
Yeah, the BASTI, well, with BASTI, I had several problems. It's not only that, they are not optimized for that. Now the most recent data release, the problem that I have there is that when you try to produce luminosity functions, you're going to have some cuts for the bright end of the luminosity function. And that's a problem, because you are going to have some models without contribution, because it's just like from 0 to everything in magnitude 10. And you know that it's not going to be like that, because you compare that with other models, and it's due to the fact that maybe they are underestimating the number of bright stars there. So that's why in the end, after comparison, because I have also tried with more models, but BASTI was one of the models that I tried. I decided, okay, let's go for other models. And with Parsec and with MIST, I found that they are independent, they are different, and they look complete in the sense that you don't see any obvious problem. And the thing is that they agree within the uncertainties that actually were estimated using this disagreement. So
okay,
now it's more robust.
Well, thanks a lot. Do we have any questions in the chat from the people, or
no obvious questions from the people from Zoom? So
okay, so let's thank Paco again.